Hello. Today I will be starting with multiple integrals. In this video I will look at just regular um, integrals with functions on them as their limits, and then integrals with polar coordinates and how to translate them into polar coordinates. Okay. So we have this function. We have a double integral of 3x squared plus a times y, and then this is and then it's being bounded by this certain paraboloids, right? So what is happening? This function is what is really happening. We're gonna find the volume of of this region. This function is the actual function. So if we have an xy plane, xyz plane, um, there's a certain function right here, right here, and then what is happening, this function is hitting this axis that it creates a certain region on the xy plane. And this region is marked here. So we want to be able to solve that. So now what we have to do is, the most important thing is choose our limits. We have a function, right? But we gotta choose our limits. So let's draw how this region looks like. So this is a paraboloid, right? A four paraboloid. So it's going to look kind of like this. And then it's going to look like a parabola, but upside down. And this is to the right here. So it's going to kind of look like this. And he's saying is that the region shared is the area that is hitting. That's the region that's going to be our limit. So how we had limits from here to here, now regions is two-dimensional, so it's going to be as an actual area. It's going to be a region. So how can we solve this? So what we can do is we can take this function and see where they meet, right? So all we have to do is set them equal to each other. So we gotta say 4x squared is equal to 5 minus x squared. So if we add this, so this will be 5x squared to 5. This will go away. This will become an x squared 1. So our region is, so where they intersect is this, well, is 1 and -1. Okay. So that's good. So now we gotta think about this. So we want to be able to translate an integral that looks like this, 3x squared. This area, right? This area is being formed by the little dx's and dy's that are happening. So the dy's are actually these little vertical lines that are happening. I'll draw a little region right here. So a little y, little dy's that are happening. I know we call them dx, but because we're treating dx as constants, the only thing changing are the y's. So the vertical movement is the thing changing. And then when we derive to dy, so we can say dy. And then the other way, then we want to look at the little dx's. So remember, the only thing changing are the x's. So we want to look at the little dx's, so dx. And another thing, we can actually change this order. We can do dx, dy, but I just like to always stick with dy, dx. But if you have an integral that's really hard to solve, you can change the order and it might make it easier to solve. Okay, so now we're doing respect to dy, dx. So remember, in dy's, we're looking at from the vertical standpoint. So from here to here. So it's easier to think about because, vertical columns are dy's. So we're going from here to here. So our function is this bottom function to this upper function. So this upper function is 4x squared, and our upper function is 5 minus x squared. And then now we want to focus our dx. Our dx always need our most outside integrals always need to be constant, right? So let's do the constant. So it's from -1 to 1, and then that's our integral. That's the setup of our integral. That's one of the most important points. Okay, so now how do we solve it? Well, because I'm integrating to respect to dy, I can just treat, so how I deal with partial derivatives, I can treat x's as regular, not as a constant. I can treat them as constant. So let's do that. So if we derive to dy first, we can do this. So -1 to 1, and then we have 3 over 2 x squared y squared. You see? And then this, we're taking the limits from 4x squared to 5 minus x squared dx. So now we can go down. So now let's let's integrate. Sorry, let's substitute in points. So -1 to 1, and so this is a constant. So 3 2, that can come out x squared, and then 5 minus x squared, and now this would be a minus this, so minus in here, so we have the x squared times 16, because this 4 became a 16, and then x to the 4th. Oh, sorry, and I forgot to square that. So that's, and then dx. So now everything is in terms of dx. So now we can integrate it normally. The best thing to do here is to simplify it. So let's let's FOIL this. So let's expand this. So this would become 3 over 2. This will become a 25 with this x squared, so 25 x squared. This will become a negative x squared 5, and then another one, so it will become a negative 10x squared, right? And then we have this x squared, so we have a negative 10x to the 4th. And then this will become this, so this would become x to the 4th, plus this, so plus x to the 6th. Then minus 16 x to the 6th dx. So now let's simplify even more. So we have 3 over 2. These things right here can actually go to negative 17 x to the 6, and then this can just stay as negative 10x to the 4th plus 25x to the 2nd dx. And now let's try to simplify it. Sorry, so now we can integrate it. So we're going to have 3 over 2. Oh, remember, -1 to 1. 3 over 2. So this will become a negative. Oh, okay. And sorry, another thing that I wanted to note is that, do you see all of these functions, right? All of these powers are odd power, are even powers. That means the area is going to be, if you do, because they have the same bounds, just opposite signs, you can actually multiply by 2 all of these, right? All of these, and get the same area. So let's multiply by 2 right away and get rid of this 2. Then now this would make it easier. Now we can just integrate from 1 to 0 and get the same thing. So negative 17 x to the 7th minus, so this would become a 5 x to the 5th 2, because 10 divided by 2, and then 25 over 3x to the third. And then that's from 0 to 1. So now if we put this in the calculator, if I put, because it's just by 1, so all we have to do is just add all of the coefficients. So we do -17 over 7 minus 2 plus 25 over 3. And then we have a total. Oh, and then we multiply that by 3. So we have a total of 82.82 over 7. So that's our overall volume. Good. So that was rectangular. So now let's go to polar. So these integrals, exact same idea. You are integrating over a certain region under this function. So this is the function that's the three-dimensional function, and this is a region. So if you notice, right, if you notice this region is actually a circle, and because it's just a positive side, it's just a hemisphere. So we can turn this whole thing into an actual integral. So we can turn this thing into polar coordinates. So remember, an x is equal to r cosine theta, and then our y is equal to r sine theta. So let's do a double integral, right? We gotta put these things into here. But look, if we put this into right here, right, this will become r squared cosine squared plus and minus r squared sine squared. That's a trig identity. So we can reduce this whole function to 25 minus r squared. This is good. So now to convert it to polar regions, you just have to remember that the end of it, the dA, instead of becoming a dx and dy, it becomes an r dr d theta. So we can plug this in here. This r can just come out right here. This, and then dr d theta. It's saying it's a region, right? This is telling us a region. So our region is a circle, which is good, because this is why we're doing polar coordinates. It's easier when like things have like some type of curvature or circle attributes to them, because sometimes it's really hard to integrate things in terms of x and y. It's just very tedious and maybe sometimes even impossible. And this is why, look, probably integrating this like just the x and the y's would be very tedious and very long. Just a little problem that we did the other like previously took us some time. So then, imagine taking those bounds that are square roots, and all of this will take a very long time. So our bounds just becomes, this r represents a radius. So this is a radius of 5, right? Is saying this is a radius of 5. So all we have to do is take, because it's dr first, so it's 0 to the square root of 5. And then our angle is a hemisphere, so it's just going all around the circle, 0 to 2 pi. Perfect. So now they just have regular constants as their, as their bounds. So now, okay, this is nice because these r squared, right? We needed for u substitution to work, we need an r right here, and we have an r. So now we can just use u substitution. So 0 to 2 pi. So this, if you derive this, you will be left with a negative 1/2. This r will go away. So we can just pull this negative 1/2, and then this will come to a 25 minus r squared all over 3 over 2. Sorry, 3 over 2. And then remember, we have to divide it 3 times 2. The 0 to square root of 5 d theta. Let's make this a little nicer. So we can have, what we can do, we can pull out this 2 and 3 out. This 2 would cancel this 2, so it will just be a negative 1 over 3, 0 to 2 pi. Then we just have 25 minus r squared over 3 over 2, 0 to square root of 5 d theta. Okay, so now we can plug this in. So 0 to 2 pi. So this 5 would be plugged right here. And then this will just become a 5. So 20. So it would be a 23 over 2. And then the 0 will just make this a 25, right? Over 3 over 2. The square root of 25 is 5 over 3. So 5 times 5 times 5 is equal to 125. So we can do minus 125 d theta. So now we can integrate this and just say, we don't even really have to put the variable on it, because this is everything is gonna go to 0. So we can just put 2 negative 2 pi over 3 is times 3 over 2 minus 125. So that's going to be the area of, the volume of that certain. So look, we had to do in rectangular. Sometimes doing polar is a lot quicker, which is nice. Okay, that's all I have. And then next we're going to go to triple integrals, and we're going to discuss about rectangular coordinates and spherical coordinates. Thank you.